Okay, so let's talk about U-substitution. So what I'm going to do in this video is start off by describing, what U-substitution is, what to do, and what to look for when doing this form of integration. And then I'm going to go into a really in-depth example, step-by-step, explaining what I'm doing, why I'm doing, everything that I am. And I call that example 0. All right? And then after that, I just do some normal examples at a regular pace, right? It's going to be a lot quicker than this. If you're just looking for those examples, I have a time code in the description that brings you straight to example 1, right? I also have a second time code that brings you straight to example 0 if you just want to skip the introduction bit and go to worked out problems, okay? So, integration by U-substitution. Before I talk about that, I just want to slightly backtrack to something you've already done, taking derivatives, right? You know how to take derivatives of basic stuff, like taking derivative of x to the fourth or cosine of x, stuff like that. But then once they got more complicated, like if you needed to take the derivative of something that looks like this, you needed special rules, right? So you learned things like chain rule, product rule, quotient rule, things like that to make taking derivatives of these complicated stuff easier. At this particular point in the course, you would have done basic integration. So that means you know how to take integrals if I just gave you something like this, 4x to the third, right? Or just the derivative of ln of x, things like that. But when it comes to stuff that looks a bit more complicated, you might be a little confused on how you go about doing that, right? You haven't encountered something like this yet. So are there things like chain rule, product rule for integrals? There totally are. The two main techniques for doing complicated integrals that you'll go through in your first or second calculus class is U-substitution, which is the main focus of this video, and integration by parts, which I'll have another video on. So, the technical definition for U-substitution, I've written out here. Now, that's not going to really make much sense to you right now. I've mainly put it there hoping that you might be connecting it to something you've already seen, right? It should look kind of familiar to something else you've done. And I'll reference that a little later, okay? So let's just start out with this first example 0. Now what we have here is the integral of 4x to the third times the square root of x to the fourth plus 5 dx, all right? And we need to take the integral of that. Now, the way U-substitution works, the primary technique in this, is taking some of your more complicated stuff and substituting simpler things that you can more easily integrate. All right? Now, the way that's going to work is typically the thing you substitute we call U, and the real trick is, like the natural question you might ask is, all right, how do we figure out what to substitute? Now, the unfortunate answer is that totally depends question to question what you're going to substitute and how you go about substituting it. That's kind of what makes U-substitution really tricky. And the general trick to that is when you're looking to do U-substitution, there might be an inside function and an outside function. And what you want to do is typically set U, the initial substitution thing, as the inside function. Now, hopefully that sounds familiar, the terms inside and outside function. It's very similar to chain rule, which kind of looks very similar to the thing right here, the actual technical definition. Because integration by U-substitution undoes chain rule, right? So let's go into the actual technique. Let's start off by figuring out our U term. Now, I always suggest to the side of your paper kind of neatly putting what your U term is. It's really important to keep track of some of this stuff because the questions can get kind of complicated. So let's set U equal to whatever our inside function is in this case. Here we have x to the fourth plus 5. So let's just set U to x to the fourth plus 5. And now what we need to do is take the derivative of U, which we'll call du, okay? And what is the derivative of x to the fourth plus 5? Well, that is 4x to the third, right? That's super simple to take. You should be experts at that by now. Now we go and substitute in these terms, okay? So I'm going to do the substitution one by one. Typically you do it all in one step, but we're going to get the integral of, well, if I substitute x to the fourth plus 5 with u, right, the thing that we made it equal to, what we're going to get is 4x to the third times the square root of u dx. Now what we have left is a 4x to the third dx, which is actually exactly what we have here, which I forgot to write the dx term. Easy to forget, but really important not to forget. And what we can do is, okay, just rearrange this a bit. Integral of square root u, and then, because multiplication is commutative, times 4x to the third dx. So you can more easily see that, okay, this stuff is equal to this stuff, and that is equal to what du is. So let's rewrite that integral as now square root of u times du, right? By just doing that substitution. Now, this is much easier to integrate than this. So let's do the actual integral. I'm going to grab a separate sheet of paper here, just because I think I'd run out of room, and take the integral of the square root of u du. Now, what would you do normally when you just had, okay, square root of x dx, right? U is just any variable now. Well, we need to change it into something that we kind of know how to integrate. And this is something we definitely know how to integrate. You should be super familiar with converting roots into fractional exponents by now. So let's take the integration of u to the 1/2 power. So what are the steps? Well, in order to do that, we have to add 1 to the exponent. So we know u is still our base. And 1/2 plus 1 should be 3/2. And what do we have to do? We have to divide or multiply by the reciprocal of what our current exponent is, right? What the new exponent is, not the original. So we have to multiply this by 2/3. And then, since we're doing an indefinite integral or an antiderivative, we have to make sure to add the constant of integration, plus c. And there we have it. We've actually done the integral. Now what we need to do, the thing that's left, is to sub back in our u term, right? We can't leave it in terms of u because our original function wasn't in terms of u. So what was u equal to? U was equal to x to the fourth plus 5. So let's make that substitution. 2/3 times, instead of u, it's going to be x to the fourth plus 5 raised to the 3/2 plus c. And that is our final answer. All right. Hopefully I was able to explain every aspect of it that could be confusing. You know, the real hard part about this is figuring out what you want to substitute. And just to talk about that a little bit, just to go over that, it's a lot like looking at it as though you were looking at chain rule. And typically you want to pick whatever the inside function is and make that u. And then from there, you want to take the derivative of that u, find du, and make your substitutions. From there, it's your simple integration, and then reverse substituting, I suppose. Another way to kind of look at it for more complicated examples that might be good to do U-substitution on is there's going to be a term that when you take the derivative of it, looks very similar to the rest of the terms in your equation, right? In the thing you're trying to take the integral of, right? Kind of how here, this function, this x to the fourth plus 5 looks very close to what I have left, which was the 4x to the third. All right, now let's look at some other functions. I'm going to go to example 1 next. All right, so here's our first example. The integral of 3x to the second times cosine of x to the third dx. So what's our first step in U-substitution? Well, we have to find the thing to actually substitute. Now, like I explained in example 0, to this side, I highly recommend you kind of keep just some space reserved for just listing your terms. It makes things neater, cleaner, easier to keep track of. Okay? So let's figure out what we're going to make u equal to. Now, like I mentioned before in the explanation, figuring out the actual substitution is the hardest part of using this method. There's no, strict rule to it, but a general guideline would be find an inside function and find an outside function, the way you would look at something with chain rule, right? And make the inside function your u. So it looks like our x to the third is our inside function. So I'm going to make that u. And next we have to find du, which is the derivative of u. And that's something super easy to take the derivative of. What's the derivative of x to the third? Well, power rule would say it's 3x to the second dx. Now from here we make our substitutions, right? So u is equal to x to the third, so we can replace this cosine x to the third with cosine of u. And I know that du is equal to 3x to the second dx, which is exactly what we have left, this 3x to the second times dx. So now this is du. Now this is something a lot easier to integrate, right? So let's go and just take the integral. What is the integral of cosine of u? The integral of cosine of u should simply be sine of u plus c, right? Because we're doing an indefinite integral. So what we have is then sine of u plus the constant of integration. All right? So last step, we have to substitute in our original u. We can't leave it in terms of u because the original function wasn't in terms of u. So now let's replace sine of u with sine of, well, what was my original u? X to the third. And that's plus c. And that would be your final answer for that integration. Right? Just as easy as that. Let's look at another example. So here we have the integral of x to the third times the square root of x to the fourth plus 5 dx. Now this will seem familiar. This is a lot like our example 0 problem, but I've modified it just a little bit. And you'll see why in just a second. What I recommend you do is, for all of these problems really, pause the video, try to work it out yourself, and if you can't get it, we'll go through it. I'm wondering how many of you will actually do that, because I don't think I would. So let's check it out. What's our first step? Well, we gotta figure out a u and a du. Easy. First, I'll put everything to the side. I'll put my u and du off to the side. So my u, I made this box way too small. I'll make a separate box for du. That'll be fine. Look at that. So my u term, I look for an inside function and an outside function, and I make the inside function my u. Here it looks like my inside function is x to the fourth plus 5. Right? That's pretty simple. Now let's find du. What is the derivative of u? Right? X to the fourth becomes 3x to the third, and, 4x to the third, and 5 just becomes 0. So we have 4x to the third dx. Now we can go and do our substitutions. So obviously this x to the fourth plus 5 can become u, but we run into a little problem. What we have left here is an x to the third dx, but our du is not x to the third dx. So what do? We could give up. That's an option. We could quit and just... But instead of doing that, instead of quitting, we can kind of manipulate this du expression. So we can make this side equal x to the third dx. How do we do that? For this example, we could divide 4 to each side. That cancels out, and I get du divided by 4 is equal to x to the third dx. And we did it. We got it. We don't need to quit. That's a stupid joke. Okay, so now we can actually do our substitution, right? What I suggest doing is for this stuff is, rather than writing du over 4, write 1 over 4 times du. It'll make things look a little nicer in the end. Okay, so let's do our replacements. So x to the fourth plus 5, I'm going to replace it with u, and that is now square root of u. And now I have an x to the third dx left. I replace that with 1/4 du. Now, since 1/4 is a coefficient, since 1/4 is a constant, I'm going to make it a coefficient up front here, and I'll put the du in the back. Now, a rule you should be familiar with by now is that constants in integration can be taken out and put to the front, right? This is a super important rule, and it comes up in other stuff too, like when you eventually do series and sequences. All right, so the 1/4 will be taken out, and I'm now left to do the integration of square root of u du. Now I want to convert this to a form that's, easier to work with, something we have a rule to take an integral of, and that's going to be the integral of u to the 1/2. And I've mentioned it before, but you should know how to do that conversion. That should be very straightforward. It's something you would have learned in algebra. Now we can take the integral. So integral of u to the 1/2 should then now be 1 over 4 multiplied by 3 over 2 times u raised to the, sorry, this shouldn't be 3 over 2, this should be 2 over 3 times u raised to the 3 over 2. And all of that is added to c, right? Which is our constant of integration in this case, right? We always tack that plus c on the end. And what we do next is we just multiply out our 1/4. And what we end up with is 1 over 6 times u raised to the 3 over 2 plus c. Okay? And that would be our final answer. So hopefully this is starting to seem a little easier. Again, it's really just doing these steps, and after that doing a very simple integration. Let's look at the next example. Here we have the integral of x times e raised to the x squared plus 1. All right, so same stuff as before. What's our first step? Identify what is u, right? I'm going to make sure I have enough room in this example by giving myself like a third of the page. So what is u? Again, let's look at as though this were chain rule. Oh, so there should be a dx here. I've totally... Why am I like this? So u is going to be our inside function, which I think it can be easily seen that it's going to be this x squared plus 1 term. Right, so that's what we got on the inside. What's going to be our du then? Well, let's take the derivative. du is equal to 2x times dx. Okay. Now, it's not exactly what we need, right? Imagine we were to replace this thing with u. What we have left isn't a 2x, it's an x. So how do we get this side to somehow become a just x? Well, we have to get rid of this 2. How do we do it? Multiply both sides by 1/2, or divide both sides by 2. It's the same thing, but it's just, a difference in the way you say it, right? So what we have left is 1/2 du is equal to x dx. Now we can do our substitution. So let's substitute. Taking the integral, we know that u is equal to x squared plus 1. So e to the x squared plus 1 should just now be e to the u. And 1 over 2 du is equal to x dx. So this x dx here can be written out as a 1/2, and I'll always write like constants up front, times dx, or sorry, du. Now, constants can be taken out of the integration and be brought to the front. And what we're left with is the integration of e to the u du. Okay. Now, what is the integral of just e to the u? It's just e to the u, right? Any function with e in it's super easy, barely an inconvenience. So what we're left with is a 1/2 times e to the u plus c. Now we have to substitute back in our x terms, our original stuff, because like I said before, we can't leave it in terms of u because our original thing wasn't in terms of u. So 1 over 2 times e raised to the x to the second plus 1 power plus c. And that's our final answer. So I'm going to go through one final example now. So this last example might look a little bit different from the previous 3. We got this 1 and 3 up here. That makes this a definite integral. And if we know how to do U-substitution with indefinite integrals, we need to know how to do them with definite integrals. It's very possible that some of you haven't seen a definite integral before. If I was teaching a calc class, I would make sure to talk about definite integrals and the fundamental theorem of calculus before I get into U-substitution. But some of you might just have bad teachers who decide to go in some order that doesn't make sense. But the actual integration should be the same. Just ignore the parts when I'm talking about bounds of integration. All right? So we need to do our substitution now. All right? We need to find a u term and a du term. So what is our u term? Well, here we have a function that you might not typically see as having an inside-outside, right? So that's not exactly what you should look for. But we do have our more complicated stuff down here in the denominator as a 5 minus x, right? And that's kind of like the tricky thing I mentioned before of how there's no hard and fast rule for determining what u is. It depends on the problem. So here we're going to make u 5 minus x. So what would our du be? Well, du would have to be the derivative of that, which is -1 dx. Now here we have a problem like the previous 3 where, okay, we can replace the 5 minus x with u, and we're left with a 1 dx, not a -1 dx. That's an easy fix. Bring the negative over to the other side. So now negative du is equal to 1 dx. Now we can do our substitutions, right? So I'll do my integration, and I'm going to suspiciously leave my bounds of integration blank for just a second. And I'm going to do my replacements. So what I have is a 1 over du, 1 over 5 minus x, which is u, so it's going to be 1 over u. And then a 1 dx gets replaced with a negative dx, negative du. Now here's the thing, we did substitution with the stuff inside our integration. We have to do it with the bounds of integration also, because these bounds of integration applied when x is equal to 1 and when x is equal to 3. We're no longer dealing with x, we're dealing with u. So when x is 1, what is u equal to? U is equal to 4. So we have to replace that. When x is equal to 3, what is u equal to? Well, u is equal to 2. So we've altered our bounds of integration that way. So notice just that the limit where u equals 4 is at the bottom. Even though it's larger than when u equals 2, which is at the top, the reason it's there is because when u equals 4, that corresponds to to when x equals 1, which is the original lower limit. So you don't need to flip these, right? It's fine when you're doing U-substitution to have a larger number in your lower limit. Okay, so now let's actually go through the integration, right? Integrating this, we can take the negative and put it on the outside, right? And we write this from 4 to 2 of 1 over u du. Now, 1 over a variable, which in this case is u, 1 over u, should be a memorized thing you kind of have down, all right? So negative stays there, and the integral of 1 over u should be the natural logarithm of the absolute value of u. And now we set our bounds of integration like this, from 4 to 2. Okay? And what's nice about this, when you're doing a definite integral, you don't have to substitute back, right? What you're going to do is you're going to replace this in here with your bounds. You don't have to bring the 5 minus x back in. So what we're going to do is do that replacement. So negative ln of 2 is going to be negative ln absolute value of 2, then minus negative ln absolute value of 4, right? Just doing those replacements. And then you could use limit rules to kind of figure out what should go where. So rewriting this, sorry, not limit rules, logarithm rules for condensing this. So I can bring the negative to the outside, and what I have left is a natural logarithm of absolute value of 2 minus natural logarithm, absolute value of 4. And this can be totally rewritten as, I'm just going to grab a separate sheet of paper, as being natural logarithm of 4 over 2, which gets us a final answer as the natural logarithm of 2. Now, I just want to go over a very small thing about the definite integral example. Let's say you didn't actually change your bounds of integration and left that as the integral of 1 to 3, right? Then you would need to replace back in your u, right? And the reason we change our bounds of integration is kind of as a shortcut, so we don't have to do these extra steps, right? So imagine I got to here, this step. My actual bounds of integration, rather than being 4 and 2, would be negative natural log of u to the original 1 to 3. And then imagine I replace back in my 5 minus x, negative ln of 5 minus x, and then to the 1, 3. Well, that's going to be equal to negative natural logarithm of what's 5 minus 3? Well, 5 minus 3 is 2. Minus negative natural logarithm. What is the absolute value of 5 minus 1? Well, that's absolute value of 4. Right, so we're getting the same numbers. The reason to change the bounds of integration is just kind of as a shortcut, so we don't need to go and back substitute or reverse substitute. However, doing that would get you the same answer. So be very careful about how you're changing anything when doing a definite integral. So let's summarize. Integration by U-substitution. It can be a pretty complicated technique. However, it's very useful in making complicated integration super simple, right? Barely an inconvenience. What you want to look out for when you're figuring out your substitution stuff, and this is something I want to hammer home, is a good rule of thumb is imagine you're looking at a chain rule problem and you're defining an inside and outside function. Make the inside function your u term, okay? Then set up a u du. When you take the du, the term that du equals might not be exactly what you want. So what you have to do is convert, like we saw in previous examples, like if I bring this over, back from example 3, right? We saw what we wanted was in x dx, but we had a 2x dx. So we divided by 2 in order to get something equal to x dx, which happened to be 1/2 du. Right? So if du doesn't equal immediately like that leftover stuff, try to manipulate that equation to get it to equal, whatever's left over, so you can do the substitution. And just that last note on definite integrals, I want to hammer home, when you're when you have those bounds of integration and you substitute the stuff inside the integral, you also should substitute your bounds of integration. And that should cover it. If you don't feel comfortable with substituting the bounds of integration, make sure you back substitute in terms of like, don't leave your answer as u and then do the integration. Make sure to replace it back with whatever u was originally. That should hopefully cover U-substitution pretty thoroughly. Hopefully this doesn't end up being a super long video, but if you have any questions or if you think I left something out that you want me to go over, leave it in the comments. But other than that, good luck.